first you need to know what is edge dislocation. So edge dislocation is a if we look at the atomic scale, it's involved an extra plane on the crystalline solid. For example, if we have okay, let's say we have this normal atomic structure. Let's say it is in cubical structure. Okay, one cube represent the 1 unit cell. This is normal. Okay, this is the normal lattice of the crystalline at the atomic scale. Okay, this represent 1 unit cell. All right, so this is a perfect structure. Unperfect structure is when we have dislocation. Okay, one of the example for the dislocation is edge dislocation. So we define this as an extra plane put on the upper block, material block. So it won't be inserted like this. It will be inserted like this. This one will be an extra. So the extra means that the original plane will be shifted. So original of the black plane will be distorted. Okay, so let's say this is an original position. So the new position will be like this. Okay, it will be distorted. Okay, the original position of this atom will move to this atom location. So it will become like this. So similar to the atom here, it will shift to this. It will looks like this. Okay, the position is slightly shifted. Oh, sorry. Okay, the new position. All right. So original atoms will distort like this. So why? Because there is an extra plane here. Okay. So this is the dislocation. So we put a symbol like this. This is dislocation. And the question here mentioned about edge dislocation opposite sign. So meaning that one having this signs where the extra planes located at the upper block of one block of material. Okay, for example, we have this one bulk material. So let's say inside there is a inside the crystal structure there is a dislocation at this direction. So opposite side means that somewhere we have here here we have facing up edge dislocation, the other region they are facing down. Okay, something like this. Okay, so let's say we have two edge dislocation, 1 and 2 different direction or opposite signs, and having slip plane that are separated by several atomic level. Okay, so let's say they are just apart with several atomic layer. So if we give some load, okay, the plane is slips, and briefly describe the effect that result when these two dislocation are become aligned. When they become aligned, one like this, we give a load, this move to this direction, what will happen? So they looks like cancelling each other. So maybe if you give a slight load at this direction, when they meet at this position, the dislocation will stop. Okay, the dislocation will stop because there are no more extra plane. Okay, so even though the load is there, but the slip is not there anymore. Okay, the slip plane is not there anymore. So at this point, just to tell you that if we want to have a zero dislocation, either we allow the slip is moving, Okay, the reason why slip can be moved when we generate heat, okay, they can arrange themselves and they will cancel each other. So there will be zero edge dislocation, zero defects in the materials. So the way that we allow this, basically we induce heat and the atom will move because there are stresses. There are stresses inside the metal. There are stresses because of this extra plane. So they will arrange themselves. Let's say there are some another extra plane somewhere here, or maybe somewhere here apart with x direction. Let's say this is x direction. Okay, we give a slight energy, which is typically we conduct annealing process. So that's the reason during the heat treatment process, we release this multiple dislocation that caused by co-working. So I remember last time one giant company producing steel wire rope. Okay, steel wire rope. So the steel wire rope, okay, before it's become a rope, it is just one single wire. Okay, the wire has gone through a drawing process. Drawing process is a kind of the code working process. So the original size is larger. When it's passing through the dies, it will become smaller, but it is packed with the dislocation, and it gives a effect of strain hardening. Okay, you need to understand this concept. Okay, because of strain hardening, the metal wire become stronger and of course harder, but it's not harder in the sense of brittle. Okay, it just increase the property in terms of the strength. Okay, because of strain hardening, it will increase strength. So once your material become high strength, you need to ensure the properties of strength is meet the design requirement. Is the value of strength of this wire after the drawing process is necessary or too much. Okay. However, remember, because of this strain hardening process, there are a lot of stresses inside. Okay, the stresses that cause materials become high strength. However, if it is too much, okay, uh, sometimes we don't want the effect of strain, okay, giving high strength. Sometimes we just want to obtain the specific crystal structure. Okay, remember after the drawing process, original microstructure is like this, and after the drawing process, it become elongate, and this microstructure also because of this microstructure it's also promote the high strength properties. So maybe we want this effect from the microstructure changes dominate the strength properties, not the multiple residual stress or strain that increase in density inside the microstructure. So maybe we can, because of the residual stress caused by the strain hardening, give a bad effect to the steel wire. So what we can do, we do the annealing process just to eliminate this dislocation. But the microstructure will still maintain as microstructure after the drawing process. Okay, we conduct maybe not 100% annealing process, just a heat treatment process to remove the residual stress. So maybe the strain will not totally reduce. Remember, if we conduct the heat treatment process, which is the annealing process, okay, this one mean that we can reverse back the mechanical properties. Okay, we don't want this to happen. We just want to eliminate the residual stress. So if we conduct a certain parameter, specific parameter for the heat treatment process, we can maintain this microstructure, but we eliminate the residual stress. Okay, so how? By doing this. Okay, allow the heat to realign the extra planes contributed by the edge dislocation. So this is what happens. You need to understand the concept. in this question. So any questions so far? Do you understand this? Do you know what is the edge dislocation, right? First, you need to know what is edge dislocation. And inside the edge dislocation, the characteristic of edge dislocation having facing up and facing down extra planes on the slip planes. And then if we induce some energy, we can having this phenomena, okay? When the opposite direction of the slip aligned with each other. So any question for question number 1?
Yeah.
Faham eh? Alright.
Betul.
Yeah. Silakan.
Ini tadi kita buat annealing. Betul kata kalau kita buat heat treatment yang annealing tu dia boleh reverse back mechanical properties kan doktor. Tapi kita tak nak kan?
Kita tak nak. Itu complete lah, complete. Ada heating, ada soaking, ada slow cooling, itu complete. Kita tahu itu fundamental yang sangat basic untuk annealing. Tetapi yang ini adalah heating. Kita apply that basic concept, heating, tetapi kita jangan buat complete annealing. Ini experience saya dengan industri tersebut. Bila kata annealing ni kita tahu alamak nanti properties dia dah tak kuat lah macam yang selepas code drawing. Sebab purpose kita buat code drawing bukan saja kita nak kecilkan saiz, tetapi kita nak utilize effect daripada code drawing process, which is kalau kita kecilkan saiz dia akan improve mechanical properties. So itu sangat typical annealing. Tetapi we understand in the annealing process, remember what is the saya tengok balik nota. Okey, sambung balik soalan awak.
Soalan saya kiranya kita tak buat annealing, maknanya kita kalau annealing dia akan reverse back mechanical property. Tapi yang kita nak eliminate residual stress sahaja kan doktor?
Ya saya.
So untuk eliminate residual stress dia punya proses dia adalah 2H dislocation doktor. Itu nama dia. Macam tu.
Salah satu fenomena dia kalau ada edge dislocation, apa yang berlaku adalah it will realign the dislocation tersebut. Okay, which is will happen at this maximum temperature, which is at 0.4 melting temperature. And then you don't have to allow the recrystallization process. Okay, because recrystallization process will, it will change from the left side microstructure like this, okay, into equax or almost spherical, okay, distort into the original microstructure. Distort is the microstructure that having high strength. Okay, distort microstructure is the structure obtained after code drawing or code working process. So if you allow recrystallization, you will eliminate the distort, the elongate microstructure. Microstructure yang pendek-pendek panjang tu kan, dia akan recrystallize menjadi yang bulat-bulat tu, yang almost equax. Equax so similar at all direction. Okay, tak ada direction ke X dia memanjang, direction ke Y dia memendek, tidak. Equax tu maksudnya dia sama je direction. So almost spherical lah. But we don't call it spherical. Spherical is a solid spherical, but equax is we consider having almost a similar size at all direction. Okay, but after the code working process, on the left side image is the microstructure that having non-equax structure. It's elongate, dia memanjang at the code drawing direction. Okay, so that microstructure is strong, but equax microstructure is soft. So we don't allow the recrystallization, meaning that at my experience with the company, we conduct the temperature similar to annealing temperature, but sometimes we adjust a bit, maybe not 0.4, maybe less than 0.4 melting temperature. We conduct, let's say, 0.38% ataupun 38% or 35% from the melting temperature, and at that particular temperature it will produce no recrystallization. Allow that temperature reach only for 10 seconds. Okay, not even more than 1 minute, not even more than 60 seconds. So you reach that particular temperature, immediately you switch off the furnace. Okay, you tutup suhu dia. That's what happened. Just experimental work, but we can see it's actually what happened. There's no recrystallization. What happened is just eliminating the trap dislocation inside. Okay, so this is what happened. Faham?
Yang maksudnya kalau yang 2H dislocation of opposite sign tu yang dia cancel each other tu, maknanya kita masa tu sekejap lah tak berbanding dengan annealing kan?
The process is occur during the increase of temperature. Masa nak reach 0 point, memang dia berlaku masa tersebut lah.
Dia sebelum constant temperature lah.
Recovery is where the program reduce their stored energy. Stored energy basically similar to the residual stress. Residual stress tu biasanya stress adalah quantitative value yang we can determine the stored energy inside after the cold working process. So what happened in the recovery, inilah dia kan masa dia ada induced heat tu kan. The first stage sebelum recrystallization adalah recovery. So the atoms will rearrange because there is a slight energy, but it's not enough to form a recrystallization. So the RAM temperature from room temperature to 0.4 from the melting temperature is the recovery process. Okay, not yet recrystallization. Faham
Okay, that's it.
Alright, very good question. Any other question before we move? Baru soalan satu And similar to the question number 2, okay, if you have a edge dislocation at different screw direction, when they meet each other, meet halfway, they will stop at that point. Okay, so this is also the similar phenomena during the recovery. Okay, same goes to the if you apply load, sometimes that particular load is not sufficient enough to promote the deformation process. Why? Because even though there's a dislocation moving inside, but at that point they just cancel each other. But if you give a very high load at one particular direction, and it's enough amount of load that promote the dislocation continuously generate and moving, okay, during this. All right, define the slip system. I think most of you know what is slip system. Okay, you can please. The reason I give you this question because all this listed here is something that you need to cover under this topic. You need to know what is slip system. Okay, do all metal have the same slip system? What do you think? Are they having the same slip system? And whatever you answer, give a reason. Okay, for example, we have copper and we have zinc. Okay, do these two materials having the same slip system? What do you think? How to find this answer? I need to know you need to answer my question during this discussion. Not exact answer, but basically because this is open book test and open-ended question, so meaning that I need to know your ability on giving some idea how you are going to find the answer, the direction of you having the answer. Okay, so for example, in this question number 4, okay, do all metal have the same slip system? How you are going to find this answer? Are you going to Google what is slip system? Are you going to what? Look at a certain properties that giving you some information on the answer?
Cari dia punya crystal structure dulu.
Yes, exactly. All right. So the characteristic of the materials can give information on slip system. For example, copper. Okay, now you want to know slip system. What is the basis for the slip system? Question number 3. Okay, it is based on crystal structure. All right, different crystal structure will give a different slip system. different numbers of slip system. For example, copper, what is the crystal structure? FCC. Okay, of course, kalau soalan tu dia kena bagi spesifik lah. Pure copper and pure zinc. So zinc apa crystal structure dia? Carilah SCP.
HCP.
Yes, SCP. So look at this FCC. What is the number of crystal structure? Okay, how to in your exam or your test, you need to answer in the essay form. So you need to explain in detail. You cannot rely 100% on the lecture notes, because lecture notes is a very brief, and in the form the notes is in the point form. Okay, so a point form, but you need to really understand and look at the. Oh, okay. Don't forget to subscribe to Dr. Habibah YouTube, because she uploaded all her video. Okay, so I've not recorded. I have some previous videos, but using the all lecture notes and all lecture content, so it's not valid for your case. But the topic almost similar. 80% is similar. Okay, but Dr. Habibah's is the recent lecture notes, so you can follow easily for her video. Okay, so you need to explain in terms of FCC. How many? Last time I showed to you the how the student answer on the different crystal structure and different slip system. So you need to be able to explain in detail what is FCC crystal structure and how it promotes 12 number of slip system. Okay, so and why larger number giving a specific property, which is data properties, as compared to the lower number in the slip system. For example, HCP having three slip plane, three slip system. Okay, contributed by one slip plane and three slip direction. Okay, so you need to give a detailed answer, not just a random answer. Okay, not random, brief answer. Okay, very brief is not applicable for the open book and open-ended question in the form of essay. Right. Briefly explain why small angle grain boundary are not as effective in interfering with the slip process as are high grain boundaries. High angle ni. High angle. Okay, small angle and large angle having a different properties. So this is mean by, okay, for example, all right. So high angle or low angle is like this. Okay, let's say this is the orientation of atom, the atom's orientation in this grain. Okay, grain 1, this is grain 2. This is the grain boundaries. Okay, so let's say this is the plane that is slipped along this slip plane, and when they meet another crystal orientation, let's say like this one, so it just require a slight energy to crossing this border. Okay, so this is the angle is shifted small. Okay, let's say this is theta 1. And what about this? If this slip direction meets another orientation at the grain boundary with higher angle, let's say like this. Okay, so the angle is larger. So theta 2 is larger than theta 1. Okay, so that's the question asks you why this is required less, is easier as compared to this one. This is because it's require higher energy to crossing the grain boundary or apa ya, to apa ya? Yeah, to cross the obstacle. Okay, so the ground boundary is the obstacle to the slip or dislocation motion. Okay, so explain why small angle boundary are not as effective. Okay, not effective. So meaning that you need to give some difficulties to the dislocation motion. So then you can have an effective um, barrier. So you can increase the strength. So one way is having large, but of course we cannot control this. The only way we can control giving the obstacle or a restriction to the dislocation motion, but by having an effective grain boundary, there's one way we control the grain size. Okay, to make this one is effective, how to make grain boundary as an effective barrier to dislocation motion is having small grain size. Okay, why? Because you give more obstacle. For example, like this. Okay, the small grain boundary. So let's say there's a lot here. So slip moving here is require more energy to change the direction, change another direction, change another direction, best depending on the cursor orientation. Okay, imagine there is a slip, need to move from one point and then change the direction out. Okay, from here change direction, change again, change again, change again. It's require multiple. It's require the dislocation to passing through multiple obstacle rather than having large grain boundary, large grain size. So how to make this grain boundary effective is having a small grain size. So we will give more obstacles to the dislocation motion for the slip to move along the grain boundaries. Okay, so this is grain boundary as an obstacle to the dislocation motion is a method to strengthen the materials. So there are several methods. One of them is utilizing the grain boundaries, because the grain boundary is normally will be present in our metal. Okay, there will be grain boundary except of single crystal. Single crystal metal, there's no grain boundary. Only one single crystal. So meaning that, for example, like silicon wafer or electronic component, the chips. What else? The turbine blades. Again, there are several materials that having single crystal. So in the single crystal, let's say this is your material. Okay. Excuse me, Fidaus. Main kat bawah, please. So let's say this is a metal with single crystal. So let's say this is the metal, the crystal orientation. It will be all at this similar direction. Okay, there's no grain at all. This is single crystal. Single crystal. So the only way you can increase the strength is by having alloying elements or yeah, something like that, because there's no grain boundaries. However, for this, if your metal, normal metal, non-single crystal metal, it will have grain boundaries. So if you want to increase the strength, you can use grain size reduction method. Okay, grain size reduction method. Okay, if you don't want to add any more alloying element, you want to use the present materials, you don't want to change the composition, but you want to increase the strength. But of course, it has a maximum limit. Okay, no matter how you make it a small grain size, there will be a maximum value of the strength. So if the maximum value of the strength that achieved by smallest grain boundaries, grain size, is not meet your design requirement, you need to find alternative. Maybe grain size reduction is not suitable. Maybe reduce the size, grain size, plus code working process or strength hardening process. Maybe. Okay. If strength hardening is not applicable, maybe straight away change the materials. Find some new materials with a specific alloying elements so you can increase the strength through the solid solution strengthening mechanism. So these are several options, because you know there are four mechanisms that we can use to increase the strength. All of you have done your project, right? Your assignment, group assignment. So I believe you have seen a lot of application on the strengthening mechanism. The third section of your assignment is how materials is being strengthened. Okay. So there are multiple methods. It can be reduced grain size, it can be strength hardened, it can be alloying element, or it can be any heat treatment. Okay. So why LCP metal are typically more brittle than FCC BCC? Okay, it is referring to the slate system. You need to explain in details. Okay. So far, do you have any problem in understanding the relationship between slip system and the crystal structure? Ada tak yang tak faham lagi? Okay, so far so good, eh? Alright. Okay, briefly cite the differences between a recovery and a recrystallization. Okay, what's the differences? Okay, can refer to the notes. Okay, what happened in the recovery? Basically, we have a process which deformed grain can reduce their stored energy. Okay, and rearrange defects. What is the defect in this content? It is a dislocation. Okay, rearrange dislocation. It can be edge dislocation or screw dislocation. Okay, or mixed between edge and screw dislocation. So what happened inside during the recovery? These two guys will rearrange themselves and they will eliminate each other. Okay. So this is a result of enhanced atomic diffusion. So why this happened? Because atoms is moving. We induce energy, they get energy, they will move faster. Without the heat, atoms have they will vibrate. Okay, at the one at their original position. Okay, they will vibrate even without the heat. So if you induce heat, of course it will vibrate at a higher frequency and higher amplitude. So that's the reason they will arrange themselves in the atomic scale. Okay. And then recrystallization is a formation of new sets of strand-free and aqueous grain. Okay, aqueous grain which is having approximately equal dimension in all directions. Okay. Right. Briefly explain why some metal, example lead and tin, do not strand harden when deformed at room temperature. Why? Okay, the reason is because it has low metal temperature. Okay, if today you do some working process, several days later, if there is some increase in the strength of these particular materials, especially pure lead and pure tin, several hours, maybe several days, it will reverse back to the original properties. Okay, senang cakap, if you ada tin solder tu kan, okay, you deform it, because it is very soft, you deform it, you don't see it will increase in strength. Okay, try to deform a wire of solder materials. You tengok macam mana pun, it will maintain the softness of the properties. Why? Because it has low melting temperature. Okay, low melting temperature, let's say solder material having 183 degrees Celsius, or maybe melting temperature for pure lead. Berapa siapa yang buat project lead ni? plumber standard. What is melting temperature of the lead? 200 something or 100 something. Okay, let's say 200 degrees Celsius. Lead. 200 something. All right. Plus 273 is equivalent 473. Okay. So degree Kelvin. So 1/3 or multiple by 0.4, you will get value there. 473 divided by 0.4 will get 189.2. This is Kelvin temperature. Kelvin temperature of the lead, okay, where the effect of annealing will occur. If you convert it into room temperature, you minus 273, what you can see, it is minus temperature of this material. So this minus temperature is even lower than room temperature. So meaning that all the time it will recover. Okay, whatever the whatever the cold working effect that you induce on this material, it doesn't give any increase in the strength. So you cannot do deformation or strength hardening for this particular material. What you can do is adding a alloying element. Then only you can increase the strength. So there are 4 strategies: reduce grain size, alloying elements, hot working, and precipitation hardening. So among these 4 methods, not all methods suitable for your alloy. You need to identify. Let's say for this pure lead, okay, there's no way you do strength hardening because it won't harden by this process. All you can do, introduce alloying elements. So how you can increase the strength of this material? Solid solution strengthening or alloying method. So you need to understand this concept, okay? So jangan simply propose method without having any knowledge, okay? The principle, the fundamental, okay, placed under this topic. This topic is very important. These 2 topics for mechanical student because you are dealing with design with various type of materials, okay? Unlike construction, unlike electrical, okay, they are more specific for specific properties, okay, which is electrical, mostly on the semiconductor, conductivity, something like that, okay, related to energy and electrical. But for you, mechanical, you are going to deal a lot of materials, a wide range of materials. So that's the reason in the 4th year, masa you ambil for the course system design, in system design, there is a one portion of topic is material selection. And a small topic. So you need to have this ability to choose material. So of course, in the real application, if you are working with a big, giant company, you won't face any problem to select a material because you can use simulation tools, okay, software to select. You just give a requirement, they will propose a suitable materials. So therefore, at the design level, you won't face any problem for that. But okay, if you are working with small company, maybe you don't have this software to automatically select the material. So what you can do is apply knowledge that you have learned in topic 4 and topic 5 of materials science. Okay, so done. Next is based on the figure below, a cylindrical specimen of copper has a ductility 15. Where is 15? Here. Okay, so your materials is copper, this is copper. Okay, not this, not this. All right, this. All right, so copper with 15, so around this 20%. Okay, so meaning that after cold working process, cold work tidak mengalami cold working process, and after the process you have 15%. Okay, if the final one is the wire kan, sebelum dia masuk size dia besar, selepas dia keluar size dia kecil. So this one is 6.4 mm and this one is X mm. and the process is giving 20% co-working. So the formula, okay, you need to understand what is the definition of co-working process. Okay, what is the definition of percentage co-working process? So the percentage of co-working process is defined by the difference in the reduction in of no, the right co-working process is the different of area before and after, which is this is final tolak, this is actual. Oh, sorry. Actual, and this is final. Okay, divided by the actual size, multiplied by 100. Okay, so so now you know it is x kuasa 2. This is radius. Okay, x kuasa 2 divided by 6.4 kuasa 2 bagi x kuasa 2. Okay, so multiple by 100 equal to 20%. So you kali lah, then you will get what is x. Okay, paling senang je lah. So maksudnya meaning that what is the radius before the deformation? It is applicable once you need to know how to use this diagram, and next you need to know what is the formula, how to define the co-working percentage. Okay, principle, before the co-working process, it having a larger size, and after you deform, it will become smaller size. The differences between the size in terms of the area divided by original size, then you can get the percentage of co-working. Okay, the larger the process, the larger the effect. Okay, so sometimes the effect will be give a disadvantage, sometimes will give advantage. For example, too much co-working will reduce very much in terms of the ductility, and if the ductility is too low, it will embrittle the materials. It will turn the material become very brittle. So that's the reason you need to set what is the optimum. Too high strength is okay, but too low ductility will give disadvantage to your materials. Okay. So differentiate between strengthening mechanism applied on the solid solution and precipitation hardening. Give example of material that use it strengthening methods. Okay. So you know what is solid solution. Solid solution is alloying. And precipitation is whatever your materials are able to produce precipitation. Okay, so this is a precipitates is the precipitates are the dislocation barrier, but alloying is a pouring atom. Pouring atoms are the dislocations barrier. Okay, how it will distort the lattice, and therefore the slip will having difficulty to slip along the slip lane. Okay, and the dislocation precipitate when it become the dislocation barrier, so it will hinder the dislocation motion at any position. Okay. So contohnya strengthening, give example, it's a very easy lah, senang sangat kan. It's too easy. Whatever, if your pure metal is copper, you add new materials, nickel, it's a solid solution strengthening, isn't it? Okay. And if you have aluminium, copper, alloy, this material able to produce intermediate, which is aluminium 3 copper or aluminium copper 3. This is a ceramic precipitate. Okay, the proper intermetallic precipitate. It can by a proper heat treatment process, you can produce this precipitate. Okay, you Google je lah precipitation hardening example metal. So not all alloy system can produce this specific alloy. Even though you have this alloy, uh, but a specific range of composition will produce precipitate. Not all composition. Okay, so whatever the composition that can produce this precipitate, it can be a materials that having uh, ha- has been gone through the precipitation hardening. Okay, number 12. In the precipitation hardening process, what will happen if we do not properly design the process? Okay, the process parameter during the aging. Okay, so now we talk about precipitation hardening. Okay, if you look at notes, I think the notes, and this is what's happening? Four methods. Spring hardening. Okay. I think I need to what. All right. Let me check. If it is not. All right. Dalamnya ada spare. Okay. So aluminum is one of the structure that apply. Heat treatment alloy. Okay. Precipitation hardening. Alloy and alloy, if we do heat treatment, okay, unlike steel, there are various of heat treatment process that dedicated for the steel. But for the non-ferrous alloy, okay, we have a heat treatment that the purpose of heat treatment basically we want to have precipitate. We want to design the precipitates. So in the precipitation hardening, this is more detailed. So don't worry about. I think all of you have covered topic for non-metal, which is in the assignment as well as in topic 10. But don't worry, it's not will specifically ask question about precipitation hardening. Okay, no question for the test tube, but final, yes, of course. Okay. All right. So what is precipitation hardening? Okay, this is in non-ferrous alloy. Basically, we apply this method, which is hardening through precipitation. So in the process, okay, this is chapter 10, which is non-ferrous, and basically this is a method where we want to increase the strength of your alloy through the precipitates. For example, the aluminum copper. Aluminum copper. This is copper. Okay, and this is aluminum. Okay, alpha aluminum. So this is 100% aluminum. Right. For this, if you have the heating process, first we conduct the heating process, solution treatment, and then we quench, and then the next step is we conduct the aging process. So aging process is quite critical because at this point we are developing the precipitates. We need to design the precipitate, the size, the number of precipitate, and so forth. Okay, so in hardening through precipitates, we are actually designing one giant chunk inside. It's not like a solid solution hardening. Okay, okay. Solid solution hardening, the atom itself become obstacle. The foreign atom itself become obstacle to the dislocation motion. How? Through the distortion of the lattice. Okay, you can see it's distort here. Okay, dia macam terangkat sikit. Okay, so if this one from this side there is a slip plane, they are smoothly moved until it reach this distort plane. It will be slowing down and then continue at the same rate and then slowing down and then continue. Okay, just small effects. But if you collect all this, okay, after edge hardening, okay, so the small particle will be a giant chunk that restrict the dislocation motion. Okay, so we call this precipitate. Right. So this is before the precipitation. This is after the precipitation. Okay. So if you have like this, if there is dislocation, it will easily move at the continuous white region, which is uh, um without precipitates. It is a alpha solid solution. Okay. So so meaning that if there's a obstacle for the dislocation motion at along this white region, it is only because of the foreign atom, solid solution strengthening. But if you have double rock block, okay, one is the foreign atom, number two is the precipitate. So you, if you want to move, there's a lot of obstacle here. Okay, the white region, foreign atom will become the obstacle to the dislocation motion. The black region is the intermetallic, the precipitate, which is very hard. You cannot easily pass in through the for this white region you can easily pass in through, but when you meet here, it is very brittle, very hard. But if it has a large structure like this, one is it gives ample region for the easiness for dislocation motion. Only at the black region will become obstacle to the dislocation motion. But over here, a lot of black particle. Okay, black particle is precipitate, so it will double up or increase more restriction to dislocation motion. Okay, so regarding to the question for the tutorials, how we need to design the precipitate, the size, the distance between precipitate, which one giving optimum. Okay, if you uh, do the experiment at a different aging time, you try, you need to know. Okay, if you increase the time, meaning that you increase the strength, but you keep increase and at some point it reduces it. So you don't need to continue the experiment. So mean because you already meet the optimum point. So this is the maximum. Why? Because what happened is increase at this point, it increased the number of precipitates. Okay, too small precipitate is not effective, but slightly larger is good. Okay, this one you can't even see the precipitate. Okay, but at a certain size, okay, for example, this one is over here. Okay, this one is too small, it's not effective at all. But if you increase the size, you can have a better strength. But too large, what happens if you have too large? Because the numbers of atoms is similar, it's not increased number of atoms, the number of elements inside your alloy is still the same. You don't add more aluminium inside your copper, you don't add more copper inside your aluminium, so meaning that the amount of elements inside is still there. Only you need to design the structure of each element inside, which is in the form of precipitate. So if you generate more precipitate at a specific size, like say like this, you can increase the strength. But if it is too large, okay, too large, what happens if you have too large precipitate size? If is you give more white region, okay, because why? Because small particle is merged. Okay, dia bergabung menjadi partikel yang besar. They are merged. Small particles are merged become large particle. So if they form large particle, what happen? They give more white region, and inside the white region is a soft properties of alloy. Okay, there's no barrier. Dislocation are slightly easy to move inside the white region. The only obstacle is a solid solution, only restricted by the distort lattice. Okay, lattice dia akan distort lah sebab dia ada alloy lagi kan, ada foreign atom, but there's no inside this white region. Okay, white region ni there's no precipitate, so more ways for dislocation to move. So there is an optimum. So that's the reason edging is very important. Over edging is not recommended. Under edging also is not recommended because there are no sufficient size of the precipitates. Okay. So what else? Okay, that's it. So that's it for tutorial 4. Any question?
No, dah.
Alright, very good. Okay, kita rehat sekejap for 10 minutes. We come back at 3:20. Boleh? Tapi ada satu lagi Instagram. Okay, kita datang balik 3:20.
那还走来走去啊，那还没有抽烟。
多少这本？
做家务。
做家务迟点做，现在
我课放第一耶。
Okay, kita sambung balik boleh?
Yeah.
Okay, alright. Okay, untuk mechanical properties ni tak susah sangat, very simple because previously all the tutorial involve how to determine elastic, plastic region, and so forth. But the thing is, that one is very basic, and I think it's already covered in many other courses like solid and solid one especially. Alright. Okay, but the concept when we talk about mechanical properties and material testing is basically we need to understand um, the behavior for metal. Okay, for metal, and of course it's also be applied for non-metal. But let's focus on the metal. All right. When we talk about properties, there are two very fundamental, which is the behavior during the deformation. Okay, the behavior of metal during the deformation. So what is it? Elastic and plastic deformation. So if we have the if we want to understand these two properties, basically we are going to uh, observe through the strain stress or stress strain curve. All right. So okay. So elastic is when we sketch the stress strain curve where we conduct through the tensile test properties, tensile test testing, we will have a typical complete plastic and elastic deformation, where at the here strength we can identify any linear stress increase with the strain. We can measure the slope, which is equivalent to E, Young modulus. Okay, so whatever the load you apply less than within this region, so it is elastic. So it will deform. Okay, dia akan melentur, ubah bentuk, it will change in shape. But whenever you release the load, it will reverse back to the original shape. Okay, so it will go through this path. Increase load, reduce, increase, reduce through this path. There's no changes on the dimension. Okay. However, if you apply load beyond yield strength, so it start to yielding. Yields mean it changed. It's go into the plastic deformation. Okay, plastic.
Doktor,
Yes.
apa beza proportional limit dengan yield strength?
Proportional limits sama lah. Proportional okay, proportional limits okay, it's slightly lower than yield strength. Okay, which is proportional limits sometimes we just use the same value, sometimes it's not similar. For example, if we have increased the loads and then okay, sometimes it will show different different value, sometimes it just use the same value. Okay, proportional limit biasanya we use for the measure the Young modulus. Sometimes it's almost similar. Okay, but usually we will use this to measure the Young modulus. Yielding means it's already go into the plastic deformation. Okay, beza sikit je. Okay, that proportional limits is a limits, maximum limits that for sure we are not entering the yield strength, yielding phenomena. Okay, so basically it is lower than, slightly lower than yield strength. Kadang-kadang susah kita nak determine pun. Okay, but yield strength basically we will we can measure by using 0.02 strain value. Okay, by using the ni lah. Okay, so these two different deformation. elastic and non-elastic, which is plastic deformation. So plastic means permanent. Permanently will show deformation. Okay. What are properties that can be extracted from the stress strain curve? Okay, one is the Young modulus, yield strength, tensile strength. This is a tensile strength, maximum limit. Fracture stress. Okay, a fracture strength, fracture stress value. What else? Ductility. Okay, ductility. What else? Can have ductility. Apa lagi yang kita boleh dapat?
Necking.
Apa dia?
Necking region.
Necking region. Okay, necking region. But necking is not properties, mechanical properties. What else? We know the necking will occur during the plastic deformation, right? But what else the properties? When we talk about, oh, I have this material, what is the properties? One is it have Young modulus, stiffness. This is stiffness. Okay, if you want to design a stiff structure, you need to look at Young modulus. You want to high fracture at a specific load. Okay, you need to look at the yield strength. And of course, high strength means that it won't deform, okay, permanently. It will, yeah, we don't look at the properties of elastic limit, but we look at the yield strength specifically. Okay, and what else? Ductility, ultimate strength, tensile strength, and also the ductility. And then apa lagi? Ada lagi tak? Tu je. What else? The property that we can obtain from the test. One single test, but we have
G. Modulus rigidity.
modulus rigidity. What is modulus rigidity? What is modulus rigidity? Why you want to have this kind of properties? Mana dapat ni modulus rigidity? Boleh dapat ni daripada stress strain curve. But what value
It's
that indicates?
Young modulus.
Young modulus, yes. Young modulus. Okay. Sometimes we talk Young modulus. Sometimes we said modulus of rigidity, stiffness value. Okay, stiffness also we use E value. Okay. And then apa lagi? Itu je. Is that all? 4 properties only.
Amount of stress.
Amount of stress. Okay. Amount of stress. Okay, if you want to sell a product, 2 materials A and B. So how amount of sell plays a role on selling your product? Okay, ada materials A and material B. Cakap macam mana? Kalau macam stiff, you can mention about E value. Kalau I mean that E value from the phase diagram, SS curve ataupun stress strain curve. Okay, sometimes we call this SS curve. Okay, stress strain curve or stress strain curve. Okay, maximum strength, we call it tensile strength. What else? Ductility, we look at the strain value. What else? Yield strength, and we get. But amount of stress, what is the parameter that you use when you talk about amount of stress? Where do you can find amount of stress in the phase diagram?
Area under the curve.
Area under the curve. Okay. Area under the curve. Actually, area under the curve, we call it toughness. Toughness. How much the energy can be absorbed by the materials. Okay. So, satu lagi, toughness. and then satu lagi fracture toughness, fracture strength. Okay, there are 6 properties. Okay, berapa banyak? 6 properties. Okay, so amount of curve is defined by the toughness. How much energy can be absorbed by the load, the materials. All right, so let's say you have this graph and this graph. Okay, so the amount of curve under this graph is less. Amount of curve under this graph is higher. And let's say you have another curve like this. Okay, you have this. So this curve, okay, even though it has high yield strength, this one is slightly low yield strength. This one is totally very low. But if you compare, okay, 1, 2, 3, 1, 2, 3. If you look at the curve, just look at the curve. What curve? Stress strength curve. Okay, between 1, 2, and 3, 2 is the highest toughness. Okay, higher toughness. Why? By looking at the graph, it is higher area under the curve. Which one is the stiffest? Most stiff, because maximum highest E, Young modulus. Okay, so also a higher strength because the yield strength is the highest. But the highest toughness is alloy number 2, and material number 3 is highest ductility. Highest ductility, because the value of strength is the highest ataupun percentage of elongation. Alright, jangan buang banyak masa. Okay. Alright, if you are required to study the mechanical properties of an unknown material, what are the possible testing method required to identify its mechanical properties? Okay, apa dia? There are so many. If you want to test the hardness, okay, hardness, we have viscous hardness. Okay, if you want to test the rigidity, ductility, strength, we can use tensor test. Okay, this one we can use tensor test. What else? Fracture toughness. We can use if you want to test the toughness properties. Okay, of course you can look at this one. You can use tensor testing method, but it's not accurate. You cannot measure exact value. Okay, toughness we can measure by impact load, impact test. Okay, this is basic for mechanical properties. Of course, there are many others, but at least through this course, you can list down this. Toughness using the impact test, Chappie, or any sample lah. Chappie, impact load dan sebagainya. Hardness, you can use Vickers, you can use Rockwell. Rigidity, ductility, strength, you can use tensor test. Okay. All right. What else? Why and how the hardenability property of a material required Jomini and quench test? Okay, Jomini and quench test we have conducted during the lab. I think most of you know what is a Jomini and quench test. You can look at the notes or Google how the method is being conducted. This one in chapter also covered in chapter 7. Okay, we have a specimen. We heat it up at the alternate phase, and then we cool it down at this one end by using water. We inject the water, okay, and then we allow the cooling happen first at this quench end and see whether the cooling effect achieved also by the distance higher than farther than the end quench. Okay, the surface that being quenched first, and measure the hardness, okay, along the specimen, and see the effect of distance or the effect of hardness on the distance between the distance from the end quench. Okay. So that's all for this topic. So any question?
Doktor,
Yeah.
contohlah kan soalan 3 ni kan dia suruh test apa-apa test lah, buat test kan untuk test dia punya mechanical properties kan. Jadinya kan selalunya kan sesuatu material tu dia akan ada banyak mechanical properties. Jadinya bila kita nak test, kita akan mention semua ke?
Tengoklah soalan tu, kalau suruh mention semua, mention lah. Kalau dia suruh mention 2, you mention 2 lah.
Okay.
Biasanya dia akan limit lah, dia takkan randomly. Tapi janganlah macam berpatutan lah. Kalau macam ni soalan ni, saya nak ensure whatever you have learned, you boleh listkan. Contohnya kalau you belajar method untuk hardness, and then what else, untuk measure strength, measure impact load, itu you make sure you answer this tutorial. Sebab saya tak evaluate your tutorials, but this is the knowledge that should be covered. For example, in the exam ataupun test, let's say dia bagi fenomena untuk this component experience cyclic load dan sebagainya. Dia bagi tahu lah properties design dia macam mana. Tiba-tiba tanya what is the mechanical properties you need to test, mechanical properties you need to study. Janganlah you cakap corrosion test ataupun you cakap test yang tak relevant. Contohnya you test the ductility ke, you measure they must be relevant. Okay, basically the test question or exam question, your answer must be relevant to the description given in the question. Okay, for example, if it's a surface that experience friction, okay, there's some friction load applied on the surface. So think about that. Okay, the surface having abrasion, dia ada surface yang bergeser. So meaning that there must be a properties that require resistant to friction, okay, or resistant to any scratching. So the properties you need to test is the hardness test. Sebab we know that the surface that can resist the friction is a surface that having high hardness. Okay, you tak perlulah test tensile strength test, sebab itu bukan properties yang you nak investigate. Okay, bila permukaan tu bergeser means that we want to test the hardness. Okay, how hard the surface resist the scratches or the penetration or indentation, something like that. So basically you need to really focus on the description written in the question. For this one is general because I want you to list down everything that's covered in the syllabus, the course content. Okay, so this one means that it's not a similar question with the test or exam, but it's the overall for the content under topic 4. So topic 4 is involved mechanical properties and material testing. Okay.
Doktor, kali ni kita perlu ikut citation ke?
Citation tak wajib sebab we already eliminate some marks for the reference. Tetapi it is good if you can let's say lah dia something yang very specific soalan dia, and then you found a very good references. So if you can because this is open ended tau, jawapan can be any. Sometimes you jumpa tetapi benda tu beyond the knowledge of the assessor, okay, the lecturer itself. Something new ke yang you dah buat, especially especially all my students have experience completing their group assignment. So you have gone through a lot of references and you have a knowledge that's additional to whatever existing knowledge that we gave to you during the class. So I'm afraid that the assessor do not have any knowledge on that. For example, the new materials, we never heard about that. Saya jangkakan lah, maybe it's not happened. Okay, so if you put references, let's say we read your answer and then we think, oh, this is, I never heard about it. If you include the references, we can easily detect. So we can easily give a full mark if it's a valid references. Okay, it's a good for you. It's just help you to validate your answer. Otherwise, maybe. Otherwise, if they don't give whatever the marks you deserve, it can be something like unfair for you. So it is good, advisable if you can include the references. But don't worry, there's no mark for that. And don't worry about the similarity because we know how to recalculate the similarity by eliminating the references during marking. Okay, you can check the similarity before you include the references, and then after you ensure it is less than 15%, and later on, if you want to submit, just include all the references. Okay, we have the second part of this diagram, tutorial 6 SEMM. Okay, this one is prepared by Dr. Habibah. She shared in the class, in her class. All right. This one is she designed this question similar to the approach that we use in the new format of material science assessment, which is using Turnitin. Okay. Right. The question is, aluminum alloy are alloys in which aluminum is the predominant metal. For example, the 2000 series of aluminum copper alloy is an aluminum alloy that typically contain between 2 and 10% copper as the alloying element, whereas copper alloy are metal alloys that have copper as their principal component. An example of copper alloy is the aluminum bronze, which is made of 6 until 12% aluminum, with the rest of composition being copper. Both alloys are extensively used in modern industrial, engineering application, but for different uses due to their different properties. Okay, give one engineering application example for the aluminum 2000 series and give one engineering specific. You need to answer one application only. Jangan bagi banyak-banyak macam tak jelas, sama-sama, ini boleh ini boleh ini boleh ini. No. One engineering component, engineering application only, and one example of aluminum bronze. Specify the composition of the host metal and the alloying element for both applications. Taking into account only the composition of aluminum and copper only. Okay. Justify why these alloys are the best choice for your selected engineering application. All right. So let's say if you want to mention about application in the for example, in the electrical industry. So specific, which part? Okay, is it the wire for transmitting the current? Okay, very specific. Jangan, do not give a very general application like for electronic industry, for the marine application, for the ship application. No, not like that. A general answer like this, like automotive is not acceptable. Okay, no. If ship mentioned, okay, ship hull, okay, or the ship turbocharger or whatever, I don't know. Okay, you should be able to find it. Electronic, what is it? Is it for the solder materials? Okay, or is it for the wire, connecting wire? Or is it or whatever? Must be specific, and you need to really clear the role. Okay, the role of the materials. Okay, like solder materials is connecting between one electronic component to the motherboard, for example, or the ship hull. The function of the ship hull to carry the load of the total load carried by the ship. Okay, to be afloat, to be especially for the to be afloat, of course, not because of the material. To be afloat on the water is because of the ship design, but mostly the materials of the ship hull is to carry the load. Okay, so it must be made of a strong material. Okay, so for the automotive, what kind of application in the automotive? Is it the bumper? Is it the main frame? Is it the metal plate for the car body? Specific, very specific. Or jet engine block. The engine block, specific. And you need to answer uh, very sure the role of the materials. Is it for just provide the protection, or is it for the carry load or impact load? Okay, so it must be very clear, because different even though in the car body you have different component, almost similar for you. You look at it, you think it's just a frame, but each frame, if structure of the frame, okay, having different properties of material. For example, in the electronic component, all of them are electronic component, but each of them act as a chip, act as a transistor, act as a capacitor. It consists of different materials, and different materials having different function and properties. So let's say the solder materials. Okay, what is it? It's a provides diffusion, okay, bonding between electronic component and circuit board. So what is the properties that make it suitable? One is conductive, another one is low melting temperature. Okay, something like that. All right. And same goes to the aluminum bronze. What is the application? And make sure you choose the application because of you highlight the properties that serve the function of that particular. Let's say aluminum bronze used for, siapa yang buat aluminum bronze? Anyone do the assignment, group assignment for aluminum bronze? Tak ada. What about aluminum copper, ada tak? Ada. Alright. Okay. So for question B, using the phase diagram provided in figure 1, trace the crystallization history of both alloy you have suggested in A. Determine the liquidus and solidus line, and determine the phase present at room temperature, the composition of the phases and their phase fraction. Okay, so let's say you, okay, there are specific composition for aluminum bronze and soalan dia. Okay, so whatever the composition, let's say you choose this composition 8%. Okay, let's say this is the choice of your alloy at aluminum. Okay, so you need to determine what is the one is liquidus and solidus line. So where is the liquidus? It is a phase separation between liquid and the intermediate phase, the neighboring phase. Okay, so this one is liquidus. Okay, liquidus, where the limits your metal will transform into 100% liquid upon heating. Okay, so this is the limit. And then this is solidus. Why is it solidus? Because it is a limit where your molten material completely transform into solid upon cooling process. Okay, so that's the limit. So determine the liquidus and solidus temperature is a temperature on this line, liquidus and solidus line. So you can just straight away read this temperature and this temperature. So for sure, okay, this is how we trace student cheating during the exam. Okay, this one maybe let's say he or she discuss with their friends, and then their friend take this one as 625. So he think that, oh, I couldn't use the same numbers, so he chose 230 degrees Celsius. Okay, at a glance I can say, oh, okay, fine, it is correct, this one is correct, this one also is correct. And then he look at his friend's answer, 548.2 degrees Celsius. He think that, oh, I couldn't choose the same number, so he chose 549 degrees Celsius. This one is totally wrong, because this is exactly the temperature that you need to take, okay, which is 540. If I found any answer like this, consider cheating. Okay, the whole answer for this, okay, for this question, let's say this is question number 3, wrong. Or maybe the whole paper will be considered cheat. All right, so be careful. Okay, so in the essay form, if you want to explain what is the temperature, okay, this one is not, of course, it is not suitable for the essay. Okay, essay, do we have this kind of question? I'm not really sure. Okay, but the thing is, the way we want to explain it, do not just give one short answer. You can explain the temperature. The temperature for liquids is a temperature where the metal completely transform into a liquid, okay, upon heating. And for this alloy containing 8% aluminum, copper in the aluminum, having liquid temperature 630 degrees Celsius. And for the solidus temperature for this alloy is a temperature where it is completely transformed into solid upon cooling process at 584.2 degrees Celsius, something like that. Okay, but basically, since you are need to determine your own alloy, so the chances on similarity will be less. Okay, because different student will have a different composition. Okay, the chances of having similar composition is less. And then the temperature of the answer, because it is open-ended question, so there's no specific answer scheme. So basically will be within the range. Okay. And then determine phases present at room temperature. So where is room temperature? Why is it only 300? Because below this temperature, there will be the same phases. Okay. So we assume at room temperature, microstructure are similar with 300 degrees Celsius. Okay. Sama je. It will be the same. Whatever microstructure that you obtain at 300 degrees Celsius, it will be the same microstructure. All right. The composition of this phase and their phase fraction. Okay, this one means at the this dia tak mention ni room temperature also lah. Room temperature. So the composition of these phases at room temperature, this alloy. So what is the phases? Phases yang ada adalah K plus theta. Okay. So what is composition? Is CK and C theta. What is it? Okay, at room temperature, let's say this is a room temperature similar to the 300. So you need to draw a tie line. Sorry, terlebih pula tie line. Okay, a tie line is from here to this one. Okay, the intercept is here, which is CK equal to maybe 1% copper. You need to write 1% copper, and bonus if you can add 99% aluminum. This is composition of K. And the composition of theta is equal to the intercept at here, which is 53% copper and 47% aluminum. Okay, this is C theta. All right, and first fraction is W. You can use P plus P, P over P plus Q multiplied by 100, and W for K. Okay, this one you know lah how to determine, right? And then the other side where the aluminum bronze, which is copper, is a main alloying element. Okay, the C. Sketch the microstructure of both alloy at room temperature. Indicate the phases at your sketch. Define the crystal structure of the phases. Using these sketches, the information on their crystal structure and unit properties of aluminum or copper. Explain how this influence the mechanical properties of this alloy. Okay. So, for example, you take aluminum copper, which is aluminum as main alloy, 8%. Okay, just now we select 8%. Oh, dah pukul 4 Sabar So, microstructure is for this alloy is contained, of course, at the, okay, imagine at this point. Look at this point. It has K phases in the liquid form. This is liquid. Okay, bukan you can lukis ni. No. Okay, I want to show you the deformation. All right, and then after it's passing through the 548 degrees, okay, whatever liquid, it will transform into a lamellar structure, which is containing eutectic structure. Okay, so below this temperature, you will get this. Okay, you have the K, primary K. This is a primary K, and then you have a lamellar structure. This is very basic. Okay, kalau you tengok sini pun lebih kurang macam ni lah. Tengok ni. Dia ada lamella, dia ada white region. Okay, it possibly like this. So why that's the reason we need to understand the principle of solidification, phase transformation. Okay, kalau you tengok soalan ni macam mana kita nak tahu microstructure ni? Macam tak pernah belajar pun dalam kelas apa semua kan. Tapi I believe all of you already understand during completing your assignment, group assignment. So the thing is, if you don't know, you need to start with a phase transformation. Look at originally in the liquid form and entering this region, there is a primary K, and then passing through this horizontal line, meaning that it will show a lamellar structure, which is eutectic microstructure. This eutectic. So tada, you got this microstructure. Okay, as simple as that. Okay, so and then you need to explain lah. There's a eutectic lamellar structure containing. Okay, in the eutectic microstructure, it consists of theta and K. Okay, as a layer by layer in the lamellar form. Okay, a layer of theta. Okay, with berselang dengan K. Right, so microstructure tu lah. Define the crystal structure of the phases. Okay, crystal structure, of course, dominant dia apa? Kalau aluminium dominant, so it will follow the microstructure of aluminium, FCC lah. And FCC and copper is same, so crystal structure will be FCC also. And then structure phases tu adalah lamellar structure. You explain semua tu And then using these sketches, the information on their crystal structure and their unique properties of aluminium and copper, explain how this influence the mechanical property of this alloy. Okay, let's explain lah FCC, ductility. Okay, ductility still can be maintained, bukan maintained lah, of course not similar. Okay, lamellar structure will increase the strength of the alloy as compared to without the lamellar structure. Okay, eutectic structure. Okay, if they have only K microstructure. Okay, if this alloy, let's say you have this alloy, okay, without the lamellar structure. it will give a different mechanical properties. Okay, let's say 2% alloy with 2%, okay, 2% copper versus 8% copper. Of course, different mechanical properties. Why? 8% copper consists of higher amount of copper, one. Number two, it has lamellar structure. Okay, lamellar structure. Okay, something like that. You can relate microstructure with the mechanical properties. Okay, microgram figure 2 belongs to aluminum alloy containing 25% of copper at room temperature. How much utility microstructure has formed just below the 500? Ni you boleh kira lah. Compare this alloy with 200 series we have sketched in C. How do the strength and ductility of this alloy differ? Thoroughly explain the strengthening mechanism for both cases. Okay, right. The microstructure of figure 2, okay, is 25%. Where's 25%? Somewhere here. Okay, this is 25% alloy. Okay, 25%. You have, if you calculate percentage of faces, okay, you need to do what you need to do. Okay, let's say you chose any, okay, above alloy adalah maksimum sampai 10% kan, 10% of copper yang you pilih in C. Whatever your chosen material in C is less than 10% of copper. Alright, so now it is 25% copper. So what you can do is determine the phase present, okay, which is K and not K, K and K, phase of K and phase of lamella, okay, eutectic. You will obtain different percentage of eutectic structure, okay, eutectic structure. So phases of eutectic structure you can determine, draw a tie line between here until here. Okay, so let's say your alloy is 8% just now. Okay, you can take P and Q is here, right? But from here to here is P, from here to here is Q. So you will get fraction of eutectic structure. Okay, so eutectic structure for this P is just this length. Okay, very short. The P short for your alloy 8%. But if 25%, okay, the P value is here. This is P for 25% and this is Q for 25%. So you will get more P if you have 25% of alloy, okay, copper. So meaning that you can have more lamellar structure, okay. So for 25% copper alloy in aluminum having large lamellar portion. So more lamellar structure, higher strength can be achieved, or something like that. So meaning that by applying knowledge on phase diagram, you can actually relate with the mechanical properties. So from that basis, you can design for the improvement. Contohnya, or now you know, okay, why my mechanical properties of my alloy is not achieved my target. So what next is having more higher lamellar structure. How to get more portion on the lamellar structure is having higher alloy composition. For example, you take 30%, or maybe exactly at the eutectic structure. So you can having 100% eutectic structure. Okay, something like that. So okay, and then for E, a main properties of aluminum bronze is corrosion resistant, which is higher than that of stainless steel, especially in seawater. However, the introduction of copper into aluminum alloy can reduce the corrosion resistance of aluminum. Explain why. Okay. So why is it the corrosion properties of aluminum plus copper is reduced. Okay, aluminum is a corrosion resistant, which is higher than siliceous, especially in seawater. However, introduction of copper in aluminum alone can reduce the corrosion resistant aluminum. Okay, so in this case, okay, we know that aluminum having a protection by having alumina. Okay, having alumina as a passive layer. So by having other alloying elements, okay, it will interrupt the formation behavior of the alumina, of the passive layer. Okay, that's basically reduce a bit a corrosion resistance of this alloy, okay, as compared to aluminum. Okay, because if it is just aluminum, it's dominant on the ability to form alumina. Means that the aluminum alloy having less bonding, but pure aluminum having less bonding as compared to aluminum bonded with the foreign atoms, such as corrosion. So with the strong bonding between the atoms, makes the ability to form passive layer less. Okay, so basically it's related to the atomic bonding strength. Okay, the bond strength between the atoms. Okay, the bond strength of aluminum, pure aluminum, bond strength is less than a bond strength in the alloy. So the formation of bond, if the bonding is less, so it will easily react with the oxygen, and if it reacts with oxygen, it will form a passive layer which protect the alloy, the materials, from further corrosion. Okay, it's not like stainless steel. Stainless steel having chromium, yes, okay, but it is still the best material is still what we call it Fe. Okay, in the seawater, this stainless steel, okay, stainless steel are not resistant to the. There's one very naughty corrosion form, okay, which is, we call it pitting. This is a type of corrosion, but it is naughty. Naughty why? Because we cannot see by naked eye. It's just a small hole, and it penetrates through the hole, and maybe it will pass into the cross section of the metal structure. Okay, maybe boleh tembus. Sometimes I have some kitchen utensil that use stainless steel. Okay, it's look very nice. There's no corrosion at all. But when I pour water inside the item, it's actually some leakage happen. But I cannot see the hole, because the stainless steel materials are not resistant to the pitting, especially at the seawater. Okay, and if there's a hole, chances of the iron to react with the oxygen is high. Okay, even though it has chromium, but chromium only active at the surface. In the hole, maybe it's not as active as the surface. So that one is stainless steel. Now we talk about the atomic bonding inside the pure metal and the alloy. So the ability to form a passive layer is restricted by the strong atomic bonding inside the alloy. Okay, so that's the reason. Okay, you relate again with the topic 1, which is atomic bonding. Okay, I think that's all for this. We have exceeded the time for today's class. Okay, right. Any other questions? All right, for tomorrow, for tomorrow test, you will be given 2 questions. One question have it's on submission platform. So have you ever, all of you have enrolled in the class for the Turning In?
Yes.
All right. So make sure you use your UTM account. Okay, make sure you use UTM account, because also at the final exam you also need to use UTM. I think all exam require you to activate your UTM account. All the final exam. Okay, you are required to use UTM account. So anyone, okay, this is a final question. Anyone still having problem, activate your UTM account. Tak ada all of you can use it. So all of you already registered, turn it in using UTM account or still having problem? What about Aaron? Aaron ada tak sini? Aaron, do you still have any problem?
Yes, doctor.
What do you mean yes?
I want to ask if because my account for test one, I can't change to the UTM account because my UTM account is already registered in a Turnitin with a Turnitin account. So do I have to register enroll again using my UTM account?
So your UTM account now you need to enroll your test 2 and because you cannot change it, all right? So anytime soon the library will delete your personal account, so your test 1 will be disappear. But I already recover all the data for the test 1. I'm not worried about that. So whatever pass is pass, but don't worry about the record in the turning in. But the record in my my record is already secured, and that record that I kept will be submit to the course file that will be stored by the university. Right. So for the test 2, I'm asking you, Aaron, whether you are able to enroll in the class for question 1 and question 2 for test 2.
Yes, doctor. I just want to confirm that because my test one is already in the past, so just forget about test one, just focus on test two and finals, is it?
All right. Okay. So all
Okay.
of you make
Yes, sir.
sure for test 2 and final exam, regardless what happened to your test 1, because I'm not really sure. They give a solution step by step, but some of the students successfully follow whatever the instruction given by the library, but some of the students having problem to follow the instruction, meaning they combine the accounts, something like that. Okay, I'm not really clear, but the thing is we have a solution for that. So we already recover all the data for the test 1. So your stored data for test 1 is secured. And then next is we move on to test 2 and final exam. Make sure you use all UTM account. Okay. I believe there are more students not present in this class today, but I hope this message reach them nicely. Okay.
Doktor, boleh minta enrollment key tu tak?
Saya dah bagi kan?
Dah bagi
Okay. Ada yang tak dapat lagi tak?
Rasanya macam doktor belum bagi.
Belum bagi
Doktor ada tunjuk kelas hari tu tapi rasa macam tak dapat lagi. Tunjuk je.
Okay, tak apa. Saya bagi hari ni. Lepas ni saya bagi instruction dia dan juga, saya present dalam tu. Saya present dalam kelas. Okay. Tak ada lagi, tak apalah. Alright, okay, saya akan share enrollment class and then ada apa-apa lagi tak nak tanya for assignment? Saya must submit by 2nd of July. And I will send you the link for assessment, peer assessment, meaning that you need to assess the contribution by the group member. Okay, it's up to you. The marks is secret. Okay, I'm the only one who knows the marks that given by your friends. Okay, you can be honest. Don't worry. Okay, apa lagi all the best to your final exam, and if the PKP ends, make sure do not forget to come and visit me anytime in my room. And what else? If you have immediately receive your appointment for vaccine, let me know, because you can get an excuse for that. I don't know, because different people will receive different side effects. I'm not really sure those outside Malaysia, but in Malaysia we can request for MC, or if you are unable to receive the MC from the person in charge or whoever at the PPV, you can keep the record of the vaccine confirmation, vaccine MySejahtera record and something like that. So make sure you have the proof, otherwise I cannot give excuse for you. I cannot make a next what we call it, a second exam or second test. Okay, because vaccination is our priority. And different people will receive different side effects. If you are okay with the vaccine, no problem. You can have the same test. You can conduct the test at the same day during the vaccine day. It's okay. But some people are not really immune to the. I mean that the antibody is not similar. Okay. Ada tak yang nak ambil vaksin? Dah register ke semua? Make sure you register. Then only we can ensure the 80% of immune apa panggil community. Okay. Okay, I think that's all for today. Kita pun dah lebih masa 25 minit. If you have nothing, I think that's all for today. And if you don't mind, please open the camera so that I can snap the photo session of our final class. Okay, boleh tak buka kamera? Saya pun kena buka lah kan. Kenapa lah saya macam ni? Sekejap kamera ni. Okay. Stop sharing. Okay, ready? Ada lagi tak nak buat kamera? Please turn on your camera. Dia tak nak bagi tahu awal kan? Kalau tak, mesti ramai yang dah siap pakai makeup Okay, ada lagi tak nak buka kamera? Please turn on your cameras. Nak kabut sikat rambut show way. Tadi baring-baring je. Okay, ada lagi tak nak buka kamera? Oh, cantiknya background tu. Okay, saya punya background ni dia tutup lah kepala saya. Okay, ready? 1, 2, 3. Okay, page 1, page 2 ready. Page 2 ready, page 2 ready. 1, 2, 3. Oh, Fikri tu dia invisible. Dia ada background saja. Okay, that's all for our class. I'm happy that the class end, but also sad because this is our last class, and yet we never met physically. But don't worry, you have another years to go, another semesters to go. You still have a chance that we can meet and we can discuss anything related to material science, especially for SKMM and SKMI, because you will have no other courses related to material. So if you have any problem with material, do not hesitate. Come and see me, and we can discuss. I'm okay if you want to ask anything. Okay. All right, that's all for today. Thank you. Bye bye, and all the best to you for final exam and testing. Yes, you're welcome.
Thank you, Radha.
Yes.
Thank you, Radha.
Thank you.
Thank you, Doktor.
Thank you, Doctor.
Yes. Welcome.
Doktor, boleh tak saya nak tanya soalan sikit?
Ya, boleh.
Contoh kan dekat sebelum ni doktor cakap yang tutorial kelas sebelum ni doktor cakap apa ni, contohlah kan material tu kalau dia low carbon kita kena tambah dengan carbon dulu sebab kita tak boleh form Martensite if the content carbon content terlalu rendah. Contoh kalau saya dah tambah, contohlah saya pilih low carbon steel. Lepas tu saya tambah carbon content melalui carbonizing process. Jadinya boleh ke lepas dah buat carbonizing process tu saya terus proceed dengan matan pering?
Boleh, ni biasanya carburizing process is a surface treatment kan. You tak boleh expect dia akan increase the whole material formation tu. So biasanya carburizing is a process for surface treatment. Okay. Dulu dalam course sebelum ni kita ada satu topik surface hardening tau. Surface hardening tu memang the next topic selepas carbon steel. Okay, the thing is in surface hardening, memang kita akan tambah carburization sebab kita nak increase dia punya carbon content on the surface. Selepas buat increase carbon content tu, okay, diffusion carbon process tu kita berlaku dalam slow diffusion lah. Maksudnya kita allow the diffuse, jadilah high carbon still dekat surface. Lepas tu kita buat surface treatment. Surface treatment tu you bakar dia punya permukaan tu pakai nozzle api yang panas, and then immediately you quench. Okay, nozzle tu dia ada dua tau. Kalau you Google flame hardening, maksudnya kita keraskan permukaan tu untuk membentuk martensite pada permukaannya. Metode kita panggil flame hardening. Okay, flame hardening tu you ada nozzle heater panas, sebelah tu pipe untuk sejuk. So dia akan panaskan, dapatkan alternate phase, and then terus quench, dapatkan martensite. So boleh, maksudnya boleh lah. Maksudnya lepas you masukkan karbon ke permukaan, you buat hardening process. Hardening tu heating, quenching and tempering lah.
So kiranya cukup sekadar quenching and
Untuk apa? Cukup tu maksudnya apa?
apa ni cukup ke kalau maksud saya boleh ke kalau sekadar actually cukup ke hanya sekadar quenching and tempering? Boleh tak kalau saya proceed dengan tempering untuk menghasilkan tempered martensite?
Oh, okay. Soalan tu saya tak tahulah you nak properties apa. So maksudnya kalau biasanya kita buat quenching, kita nak dapat hardness. Sometimes hardness tu terlampau brittle. Tetapi kalau brittleness is not main issue, so maksudnya dia just resist, dia akan support load in compression dia tak ada impact load langsung, tak ada apa. Tapi you nak hardness yang setinggi itu, you tak perlu tempering. Tapi biasanya most application dia ada mild tempering lah sebab kita nak eliminate accidental load. So walaupun dia hanya ada support load saja, kita tak risau on the impact load dan sebagainya, tetapi still kita boleh eliminate possibility on the accidental brittleness dominated by martensite. So you cukup ketat tu you kena ada complete set of problem lah baru saya boleh cakap cukup ketat. Tetapi if you think I don't know, maybe your question is based on answering the question for the test or exam. So your answer must be give a justification. For example, whatever I've explained earlier, I said that okay, if the hardness is meet the requirement, for example, the highest hardness need to achieve by quenching process, and only the quenching process can support give the value of that particular hardness, and the structure is experience compression loads. There's no issue on the accidental or impact load. The quenching process is sufficient. And if you think that the component, the engineering component, having some of the other than static compression load, martensite need to be tempered so that we can of course the hardness will be reduced, but the toughness will be increased. The brittleness will be reduced. So the explanation must become with justification dan must be relevant lah. Janganlah you benda tu guna untuk gear, you kata impact load tak important. Memanglah salah. Okay. So benda yang macam very obvious memang akan ada that particular effect, you kena make it make sense lah you punya answer. So kalau you tanya perlu ke tak tempered martensite, perlu kalau memang very obvious that particular component ada requirement for that dia punya function lah. Ada impact load, ada static load, dynamic load. Benda macam tu kena very jelas lah. Okay, jadi bila you nak design sesuatu, mesti you tahu apa design requirement dia kan. Maksudnya kalau you design komponen untuk gear, design requirement dia apa, macam mana fungsi dia. You kena tahulah, jangan you ambil contoh yang you tak jelas macam apa tu jawapan-jawapan test 1. Dia bagi nickel carbide, benda yang dia tak tahu apa nickel carbide tu. tak payahlah. You bagi benda yang you tahu dia berfungsi macam mana. Okay, contohnya macam even saya tengok jawapan student untuk alat instrumen untuk muzik pun tak logik. Padahal the reason kita pakai alat muzik tu adalah untuk dapatkan sifat getaran bunyi kan. Bunyi tu datang pada getaran. So mestilah something yang having that serve that particular design requirement. Ini tidak. Gitar wire tu dia kata wire tu sebab boleh conducting elektrik. So gitar elektrik kalau wire tu conduct elektrik dia tak patutlah kan dia pakai. Jadi kena tahu fungsi dia apa. Okay, contohnya kalau design dia untuk gear kita tahu kan. Gear tu untuk change the carry load of course, and then change the transmit the load lah, transmit the load. Okay, transmission system kan. So gear tu mestilah dia ada bergeser, dia ada bergerak, dia carry load, dynamic load. Jadi tak boleh lah hardness mata-mata kan. Dia mestilah something else. Okay, kenapa you perlukan hardness? Sebab dia permukaan yang bergeser. Kenapa you kat permukaan dia? Sebab kat dalam dia mestilah high toughness steel. Kalau high hardness dia tak toughness. So toughness mestilah dimiliki oleh the whole component. Tetapi hardness hanya pada surface. Jadi bila you cakap perlu ni kena tahulah. Okay, surface itu adakah terkesan dengan impact load. Okay, kalau surface tu tak ada kena-mena dengan just friction, tak ada impact load, just bergeser saja macam sliding surface macam komponen yang melibatkan sliding, dia tak ada pun load yang macam apa panggil kalau macam dekat you tengok kilang-kilang ada conveyor yang melibatkan sliding benda-benda heavy kilang yang heavy, dia akan ada dia apply cuma tanpa ada mechanical work untuk moving one part to another part. So the sliding part tu bergeser saja tapi tak ada impact load, tak ada carry apa, just a static structure saja. Itu bolehlah you consider high hardness saja, tidak melibatkan toughness. Tapi tak logik, memang tak logik pun. Semuanya mostly akan ada orang kata apa akan guna tempered lah. Kalau just mutton side saja very minimum lah dia punya application. But you have to very clear lah you punya component tu serve untuk apa.
Faham doktor. Lepas tu kan doktor, contoh kan low carbon steel ni kan dia tak boleh form mutton side kan sebab terlalu rendah kan. Kalau kan biasanya hardenability tu maksudnya kita the ability to form mutton side. Jadinya kalau low carbon steel ni dia untuk hardenability dia terlalu rendah ataupun tak ada. Macam saya keliru.
Hardenability tu rendah tu relatif lah. You kena tahu lah rendah daripada apa. Okay.
Kena compare lah.
Rendah tu memang rendah lah sebab dia unable secara general. Alloy steel high hardenability. Okay. Tetapi kalau dari segi kuantitatif you boleh tengok dari segi dia punya S-curve ataupun TTT diagram. Ability to form molten salt at a prolonged quenching time. Okay. Itu satu indikator. And then ability to form molten salt due to the present sufficient carbon. Okay, more carbon, more molten salt lah. Okay, itu satu aspek carbon content. And then another aspect is TTT diagram. Bila dia kata bila these two elements, okay, bila these two element di okay, apa yang saya nak cakap bila petang-petang ni dia jam. Okay, low carbon jelas maksudnya kalau low carbon kuranglah molten salt dia. Okay, hardenability basically hardenability is more close to alloy. Okay, alloy and of course apa nak cakap carbon, one reason is amount of molten salt. Okay, and I'm not really sure the S curve for low carbon and high carbon. Is there any different or not? Kalau ada different, means that hardenability of that particular different carbon content. Saya tengok high carbon and low carbon.
Doktor boleh tak doktor share TTT diagram untuk
Apa dia?
Doktor share sekali hypoeutectoid. Sebab saya kan semua TTT diagram sama. Rupanya bila saya study lain-lain. Tu saya macam keliru sikit.
Okay, dia malah lain lah. Sebab kalau you tambah any elemen, dia akan pindahkan curve tu jalan-jalan. Okay, fasa dia pun lain-lain. So kalau you compare low carbon dengan high carbon, ada tak different dia punya maximum, dia punya nose tu, hidung dia tu paling maximum tu kan, masa dia paling rendah berapa? Pernah tak you compare? Kalau you compare TTT diagram dia,
saya study yang hypo. Sebab ada kawan saya dia tunjuk dia punya tutorial kelas. Lepas tu saya macam tak tahu, macam tak faham sangat benda tu. Kalau saya tunjuk kat doktor boleh?
okay, boleh tunjuk.
Dia punya soalan. Macam nak hasilkan benda ni. Jalan dia nak menghasilkan macam ni kan, dia ada bagi, dia tak cakap berapa nilai tapi kita boleh estimate dari sini berapa persen martensite, ferrite dengan pearlite kan. Lepas tu daripada sini ni saya tak faham untuk apa line ni, saya kurang jelas. Contoh kan doktor, kalau ini kan proeutectoid ferrite begin kan, lepas tu dekat sini N. So kiranya kalau saya proceed yang line yang ini sampai melebihi line yang ini, besarkan je. Dengar tak?
Okay.
Kalau saya proceed yang line ni melebihi line yang ini, dia akan jadi 100% proeutectoid je.
Mana boleh, sebab dia akan campur eutectoid juga tu. Okay, kalau alloy ni, saya kata ni alloy yang dibagi kat atas, cuba tengok microstructure tu. Okay, dalam microstructure ni, pearlite dia berapa persen?
60%.
Tak mention kan?
Dia tak mention, macam kita agak je mungkin.
Okay, so misal katalah alloy dia tu mengandungi kalau at room temperature, proeutectoid dia ada berapa persen. So maximum kalau dia transfer into proeutectoid, banyak tu je. Okay, so kalau you tengok line ni kan, contohnya kalau
Ni ke?
dia takkan dapat apa tu 100% proeutectoid, sebab proeutectoid tu memang ada limit portion, sebab the rest akan jadi pearlite. Slow macam mana pun you buat, you akan dapat proeutectoid dengan ferrite. Kalau you tengok diagram tu, is there any region yang you akan dapat 100% proeutectoid?
Tak ada.
Ada. Atas 727. Betul tak? Atas 727. Bawah daripada tu memang akan ada pearlite. Okay, 727 masih lagi belum reach room temperature. Bawah daripada 727 you akan dapat pearlite. Okay, campur dengan proeutectoid lah. So maksudnya kalau you nak dapat maximum proeutectoid punya percentage, okay, you akan dapat if you quench to around just likely 727 lah, mungkin 700 ke atau 710 ke, and then you soak until 20 second ke, 30 second ke, even 100 second pun tak apa, and then you cool at room temperature, the remaining austenite will turn into ni lah pearlite. Tetapi tak guna pun you buat macam tu, sebabnya kalau you just normal cool at room temperature, normal furnace cool tanpa quench kepada 700, kita tak akan dapat amount yang sama lah. Okay, tetapi ni proses yang ditunjuk line ni adalah bila you nak design hanya certain je proeutectoid, the rest martensite. Kita tak cakap pasal proeutectoid dengan pearlite sebab itu you boleh dapat kalau you tak payah tengok ni pun tak apa, you slow cool je, you panaskan furnace sampai austenite and then slow cool, you tetap dapat, you tak akan dapat protracted dan pelite.
Kira macam protracted ferrite ni jarang digunakan lah.
Okay, sorry. So maksudnya sekarang ni bila you nak certain amount je protracted tu, tetapi yang lebihnya tu martensite. Sebab kita tahu protracted ni soft, tetapi martensite tu hard lah. Ni kalau you nak lah properties ni kan. So boleh kita buat dengan cara kita quench kepada protracted. You boleh quench selagi temperature first temperature quench tu bukan bawah 550, maksudnya you boleh dapat protracted ferrite. Okay. So alpha tu maksudnya protracted ferrite lah. So if you quench above 550, you still boleh dapat. So kalau final result you nak dapat protracted ferrite, you mesti quench dalam ni 650. You akan soaking for holding at that particular temperature for 1 or 2 seconds, and then quench to room temperature, barulah you akan dapat apa tu orang panggil 50% martensite. Oh, tetapi dalam ni dia apa ni? Oh, okay. Ini kat sini dia ada sedikit tricky ni. Dia nak 50% lagi yang remaining. Okay, first dia nak protracted, and then dia nak pelite okay. So alpha plus Fe3C tu adalah pelite ataupun binite, depending on the quench temperature lah. So cuba tengok microstructure atas tu. Pelite ferrite martensite kan. Dia cakap pelite kan, tak cakap binite kan. Okay. Sepatutnya binite ni. Sebab second temperature yang dia quench tu adalah region binite.
Jadi kalau even untuk hypoelectroid, dia punya nilai kat sini macam tetap sama. Kalau sini adalah pelite, bawah ni binite, terus bawah ni martensite. Sama juga macam
sama. Cuma curve dia tu lari-lari sikit, dia takkan sama. Sebab cuba awak tengok phase diagram yang sebelah kanan ni, draft phase diagram kan lain kan limit temperature dia. So of course dia berlaku pada temperature yang lain-lain.
Lepas tu kan, doktor lagi satu saya keliru kat sini contoh lah. Kan kat sini kan dia dah quench kan. Lepas tu dia nak proceed dengan
Bukan macam tu. Ini just hari tu saya ada explain yang untuk pelite dengan binite. Tapi kebetulan dia ini just schematic je. Sebenarnya dia tak ada undur pun masa tu. Kalau dia just nak tunjuk macam mana dapat cakap
dia nak gerak daripada kosong sampai berapa second.
Ya betul. Just simbolik je. Once you quench ke 650, lepas tu you quench ke 450 ni, reading time dia adalah sekian. Bila dia turun ke suhu bawah, dia akan start kosong masa hingga berapa second. Macam tu.
So,
jadi secara simbol dia tak adalah undur masa. Tapi kalau you lukis daripada 650 tu, you terus turun ke